And imagine you are standing in the aisle of a hardware store, selecting a fuel for your home heating system. On the shelf, you see three distinct products. The first is a thick, amber heating oil, the kind that has reliably warmed homes for a century. It pours easily into a tank, stays liquid at room temperature, and packs a lot of energy into a modest volume. The catch: if you run your furnace for years without cleaning it, the burner nozzle will accumulate a layer of carbonaceous gunk, and the heat exchanger will develop a stubborn film of soot. The second option is a high-octane racing fuel, so volatile and potent that a single tank can propel a vehicle farther than any other chemical. But this fuel must be stored at temperatures so low that it boils away in the open air, and its molecules are so minuscule they can seep through the walls of an apparently solid metal container. The third option is a fuel that sits between these extremes. It is cleaner than the heating oil, more compact than the racing fuel, and it can be stored at a temperature that, while cryogenic, is not so extreme that it requires exotic materials. This is the propellant choice facing a rocket engine designer, and it is the foundational architectural decision that shapes every subsequent engineering trade. And in the rocket business, the three fuels on the shelf are RP1, a highly refined form of kerosene, liquid hydrogen, and liquid methane. Each occupies a distinct point in a multidimensional trade space that includes energy content, density, storage temperature, combustion cleanliness, and the complexity of the engine systems required to handle it. For the Raptor 3, SpaceX chose methane, a decision that broke with the company's own heritage. The Merlin engines on Falcon 9 burn RP1, and with the broader industry's historical preference for either kerosene or hydrogen. To understand why, we must first understand the character of each fuel, not just as a set of numbers in a textbook, but as a living substance with its own quirks, limitations, and demands on the machinery that must contain and combust it. And RP1, the sturdy workhorse with a dirty secret. RP1 is the diesel of the spaceflight world. It is a highly refined kerosene fraction, distilled from crude oil, and then subjected to additional processing to remove sulfur, aromatics, and other compounds that would polymerize into gums and varnishes under the intense heat of a regeneratively cooled combustion chamber. At room temperature, it is a clear, oily liquid with a density roughly 800 kilograms per cubic meter, similar to that of water. This density is its greatest asset, because a given volume of RP1 contains a large mass of fuel. The tanks that hold it can be relatively small, and the turbopumps that feed it can be compact. The Falcon 9's first stage, with its 9 Merlin engines, is a testament to the virtues of a dense propellant. The rocket's diameter is a modest 3.7 meters, yet it carries enough energy to deliver over 22 metric tons to low Earth orbit. And the handling characteristics of RP1 are equally benign. It can be loaded at ambient temperature, it does not boil off, and it can sit in a tank for days without significant losses. For an operational launch vehicle that must be transported, erected, and held on the pad through weather delays, these are enormous practical advantages. The infrastructure is straightforward. Standard aluminum alloys, common seal materials, and conventional pumping equipment all work without complaint. In the language of operations, RP1 is a low-maintenance fuel. But RP1 has a fundamental flaw that becomes intolerable in a fully reusable engine. When kerosene burns, it does not combust as cleanly as a simple hydrocarbon formula would suggest. The combustion process produces not only carbon dioxide and water vapor, but also a spectrum of heavier hydrocarbon fragments, polycyclic aromatic hydrocarbons, and under certain conditions, elemental carbon in the form of soot. In a one-and-done expendable engine, this soot is a minor nuisance. It deposits on the interior surfaces of the turbine blades, the injector face, and the combustion chamber liner. But the engine is discarded after a few minutes of operation, so the accumulation never reaches a problematic level. And in a reusable engine like the Raptor 3, designed for hundreds of flights with minimal refurbishment, soot is a showstopper. Carbon deposits build up in the narrow cooling channels that line the combustion chamber and nozzle, reducing heat transfer and creating hot spots that can lead to burn-through. Soot fouls the intricate passages of the injector, altering the spray pattern and potentially triggering combustion instability. It coats the turbine blades, changing their aerodynamic profile and reducing pump efficiency. Removing these deposits between flights would require disassembling the engine and mechanically or chemically cleaning its internals, a process that would destroy the economic case for rapid reuse. SpaceX learned this lesson firsthand with the Merlin engine, which, despite being a marvel of reliability, requires significant inspection and cleaning after each flight. The Falcon 9 first-stage boosters return to port with their engine bays streaked with soot, a visible reminder of the fundamental incompatibility between kerosene and a maintenance-free reusable architecture. And beyond the soot issue, RP1 imposes another constraint. It cannot be used to cool the engine's hottest components above a certain temperature, because it begins to thermally decompose into carbonaceous residues inside the cooling channels. This phenomenon, known as coking, limits the maximum chamber pressure and thus the engine's overall performance. For the Raptor 3 target of 350 bar chamber pressure, a regime where heat fluxes are staggering, RP1 would simply cook itself solid in the cooling jacket, blocking the flow and destroying the engine in seconds. And liquid hydrogen, the ethereal sprinter. If RP1 is the diesel workhorse, liquid hydrogen is the Formula One race engine, breathtakingly powerful, exquisitely engineered, and utterly unforgiving of compromise. Hydrogen is the lightest element in the universe, and in its liquid form it has a density of only 71 kilograms per cubic meter, about 1/14 that of water and 1/11 that of RP1. To visualize this, imagine a gallon of milk. A gallon of RP1 weighs about 6.6 pounds. A gallon of liquid hydrogen weighs barely half a pound. The energy content per unit mass, however, is extraordinary. The combustion of hydrogen with oxygen releases roughly 13 megajoules per kilogram, compared to about 10 megajoules for RP1. This yields a specific impulse, the rocket equivalent of miles per gallon, that can exceed 450 seconds in vacuum, a figure that no hydrocarbon can approach. And the cleanliness of hydrogen combustion is absolute. The only exhaust product is superheated steam, with no soot, no carbon monoxide, and no unburned hydrocarbons. From a reusability standpoint, hydrogen is a dream. The engine internals remain pristine, and the cooling channels never clog. The Space Shuttle main engine SME, which burned hydrogen, could be refurbished and reflown multiple times without the soot-related headaches that plague kerosene engines. But hydrogen's ethereal nature introduces a host of problems that cascade through the entire vehicle design. The first is its temperature. Liquid hydrogen boils at 20 Kelvin, just 20 degrees above absolute zero. At these temperatures, ordinary materials behave strangely. Many metals become brittle. Seals that are pliable at room temperature turn to glass. The hydrogen molecules themselves are so small and energetic that they can diffuse into the crystal lattice of metals, causing a phenomenon known as hydrogen embrittlement that can lead to sudden, catastrophic cracking. The plumbing for a hydrogen engine must be fabricated from specialized alloys, with welds inspected to nuclear-grade standards, because a leak that would be trivial for kerosene can become a raging fire in the presence of an oxidizer. And the second problem is density. Because liquid hydrogen is so bulky, the tanks that contain it must be enormous. The Space Shuttle's external tank, the iconic orange cylinder that dominated the vehicle's silhouette, was primarily a hydrogen tank. For a given mass of propellant, a hydrogen tank requires roughly 11 times the volume of an RP1 tank. This volume translates directly into structural mass. Larger tanks must withstand greater aerodynamic loads. They require more insulation to limit boil-off, and they present a larger surface area that must be protected during re-entry. The dry mass of a hydrogen-fueled stage is inherently higher than that of a kerosene stage of equivalent propellant mass, eroding some of the specific impulse advantage. And the third problem is boil-off. Even with the best insulation, heat inevitably leaks into a cryogenic tank, causing the liquid hydrogen to vaporize. The gas must either be vented, wasting precious propellant, or actively reliquefied with heavy and power-hungry refrigeration equipment. For a mission that requires the vehicle to loiter in orbit for days or travel to Mars, boil-off is not a minor inconvenience. It is a mission-limiting constraint. The Saturn V upper stage used hydrogen, but it had to complete its translunar injection burn within hours of launch because the hydrogen would not wait. And finally, hydrogen is a nightmare for turbopump design. To pump a given mass flow rate, a pump must handle a volume flow rate that is inversely proportional to density. A hydrogen turbopump must move 11 times the volume of a kerosene pump to deliver the same mass. This requires enormous, multi-stage turbines spinning at extreme speeds, with all the attendant challenges of bearing design, rotor dynamics, and cavitation control. The SME high-pressure fuel turbopump was a 3-stage centrifugal machine that operated at 35,000 RPM and generated 70,000 horsepower in a package the size of a small suitcase. It was a miracle of engineering, but it was also the single most troublesome component on the entire vehicle, requiring endless development to tame its propensity for blade cracking and subsynchronous whirl. And methane, the Goldilocks molecule. Liquid methane occupies the sweet spot between these two extremes. Its density, at around 422 kilograms per cubic meter, is roughly half that of RP1, but 6 times that of hydrogen. This means that methane tanks are larger than kerosene tanks for a given propellant mass, but not impractically so. The structural penalty is manageable, and the vehicle can still be designed with a reasonably compact form factor. For Starship, the 9-meter diameter stage carries 1,200 metric tons of propellant in an integrated tank structure that, while enormous, does not require the absurd volume fractions of a pure hydrogen design. And methane's boiling point of 111 Kelvin is a gift to the propulsion engineer. It is cold enough to be cryogenic, but it sits in a temperature regime that is far more benign than liquid hydrogen's. At 111 Kelvin, methane is close enough to liquid oxygen's 90 Kelvin boiling point that the two propellants can share a common bulkhead in the tank without an elaborate insulating barrier. In the Starship, the liquid oxygen and liquid methane tanks are separated by a single domed structure, with the methane on one side and the oxygen on the other. The temperature differential across this dome is only about 20 degrees, which minimizes thermal stresses and simplifies the tank design. This co-location of propellants at similar cryogenic temperatures is a key enabler of the integrated vehicle architecture. And from a cleanliness perspective, methane is a revelation. Its molecular structure, a single carbon atom bonded to 4 hydrogen atoms, is the simplest possible hydrocarbon. When it burns, it produces carbon dioxide and water, with a minimal tendency to form soot or complex hydrocarbons. Under the right mixture ratio and combustion conditions, methane combustion can be virtually soot-free. This means that a methane engine can be reused hundreds of times without the carbon buildup that plagues kerosene engines. The cooling channels remain clear, the injector stays pristine, and the turbine blades do not accumulate deposits. For a vehicle like Starship that is designed to fly multiple missions with turnaround times measured in hours, this is not a nice-to-have. It is an absolute requirement. And methane also excels as a coolant. In a regeneratively cooled engine, the fuel is circulated through channels in the combustion chamber wall before being injected, absorbing heat that would otherwise melt the structure. Methane's high specific heat capacity and its resistance to coking allow it to absorb enormous thermal loads without decomposing. In the Raptor 3, methane is used to cool the entire combustion chamber and nozzle, and it does so at heat fluxes that would turn RP1 into a solid carbon plug within milliseconds. This cooling capacity is what enables the engine to operate at 350 bar chamber pressure, a regime that pushes the limits of material science. And there is one more advantage that methane offers, and it is uniquely aligned with SpaceX's interplanetary ambitions. Methane can be synthesized on Mars. The Martian atmosphere is 95% carbon dioxide, and the planet's surface harbors vast reserves of water ice. Through the Sabatier reaction, carbon dioxide and hydrogen derived from water electrolysis can be combined to produce methane and oxygen. This means that a Starship on the surface of Mars can refuel itself using locally sourced materials, without requiring a supply chain of tankers stretching across the solar system. No other practical rocket fuel offers this capability. Hydrogen can be produced on Mars as well, but its storage and handling challenges make it far less attractive for a return vehicle. RP1, as a refined petroleum product, cannot be manufactured off-Earth without an entire fossil fuel industry. Methane is the only fuel that simultaneously satisfies the demands of high performance, reusability, and extraterrestrial resource utilization. And the trade space, specific impulse versus density impulse. To appreciate the full logic of the methane choice, we must introduce the two figures of merit that dominate propellant selection: specific impulse and density impulse. Specific impulse, denoted ISP, is the measure of how efficiently a rocket engine converts propellant mass into momentum. It is the thrust produced per unit weight flow rate of propellant, and it has units of seconds. A higher ISP means that a given mass of propellant can produce a greater total impulse, allowing the vehicle to achieve a higher velocity change. Liquid hydrogen delivers the highest ISP among practical chemical propellants, typically 440 to 460 seconds in vacuum for a well-designed engine. RP1 achieves 350 to 360 seconds. Methane splits the difference at 370 to 380 seconds. On ISP alone, hydrogen wins decisively. But ISP is not the whole story. A rocket must carry its propellant in tanks, and those tanks have mass. The volume of the tanks, and thus their structural weight, is driven by the density of the propellant. This is where density impulse, the product of specific impulse and propellant density, becomes critical. Density impulse tells you how much impulse you can pack into a given tank volume. For a volume-limited vehicle, a high-density impulse is more important than a high ISP. Consider the analogy of a backpacker preparing for a long trek. She can choose between two trail foods: light, fluffy popcorn or dense, compact energy bars. The popcorn has a high specific energy per kilogram. It's all carbohydrates and air, so a kilogram of popcorn provides plenty of calories. But a kilogram of popcorn fills an enormous sack, and she can only carry a backpack of limited volume. The energy bars, while slightly less calorie-dense per kilogram, pack tightly into a small space. If her backpack volume is the limiting factor, she will choose the energy bars and end up with more total calories for the journey. In rocketry, RP1 is the energy bar. Its density impulse is high because its density more than compensates for its lower ISP. Hydrogen is the popcorn. Its ISP is stellar, but its density is so low that the vehicle's tank volume, and thus its dry mass, explodes. Methane is the carefully engineered trail mix, a balance of density and specific energy that optimizes the overall system. N for a booster stage that operates within the atmosphere and must lift its own mass against gravity. Density impulse is often the dominant consideration. This is why RP-1 has been the fuel of choice for first stages since the dawn of the space age. The Atlas, Titan, Saturn V's first stage, Soyuz, and Falcon 9 all burn kerosene. For an upper stage that operates in vacuum and requires maximum delta V, ISB becomes more important, which is why hydrogen upper stages are common Centaur, Saturn V's SIVB, the shuttle's main engines, though those were sustainer engines. Methane's intermediate position makes it a uniquely versatile fuel that can serve both roles effectively. A single engine design with a single propellant combination can power both the booster and the upper stage of a launch vehicle, simplifying development, manufacturing, and operations. And why SpaceX walked away from RP-1. Given SpaceX's deep institutional knowledge of kerosene engines, the Merlin 1D is one of the most reliable and highest thrust-to-weight engines ever built. The decision to abandon RP-1 for the Raptor was not taken lightly. It was driven by the uncompromising requirements of the Starship architecture. Full reusability with minimal refurbishment ruled out RP-1 by itself. The soot problem alone was sufficient to disqualify kerosene, but the coking limit on chamber pressure sealed its fate. The Raptor 3 350 bar chamber pressure, which is necessary to achieve the thrust-to-weight and efficiency targets for a fully reusable super-heavy launch vehicle, is simply beyond the thermal limits of RP-1 cooling. And hydrogen was considered and rejected for the booster application because of its abysmal density impulse and the operational complexity of managing a deep cryogen on a rapidly reusable vehicle. The image of a Starship booster returning to the launch mount with a cavernous hydrogen tank, its insulation still steaming, and its plumbing requiring meticulous inspection for embrittlement cracks, was incompatible with the vision of airline-like operations. Hydrogen remains a brilliant upper-stage fuel, and it may yet play a role in future deep space stages, but for the integrated two-stage Starship system, a single fuel for both stages was overwhelmingly advantageous. And methane emerged as the only propellant that satisfied the full set of constraints: high performance, high density impulse, clean combustion, excellent cooling capacity, benign handling relative to hydrogen, common bulkhead compatibility with liquid oxygen, and the potential for in situ production on Mars. It is the fuel that allowed SpaceX to design an engine that is simultaneously a high-thrust booster machine and a high-efficiency upper-stage machine, with a single set of turbomachinery, a single injector architecture, and a single supply chain. And the choice of methane, then, is not merely a technical footnote. It is the decision that made the Raptor 3 possible. It shaped the engine cycle, its materials, its cooling architecture, and its control strategy. In the blueprint of a rocket engine we explored earlier, the propellant is the first annotation on the blank sheet, the selection that determines the size of the pumps, the shape of the injector, the thickness of the chamber walls, and the very nature of the combustion process. By choosing methane, SpaceX committed to a path that demanded new manufacturing techniques, new alloys, and new control algorithms, but it also opened the door to a level of reusability and performance that no kerosene or hydrogen engine could match. And with the fuel selected, we have answered only half of the propellant question. A rocket engine is a dance between two partners, and the fuel is only one of them. The other is the oxidizer, the substance that releases the energy locked within the fuel's chemical bonds. Without it, methane is just a cold, inert liquid. With the right oxidizer, it becomes a controlled explosion capable of hurling a spacecraft to another world. That oxidizer is liquid oxygen, a substance so reactive that it can set fire to materials that are not normally considered combustible. And it is the subject of our next section, 2.2 liquid oxygen LOX, the invisible fire starter.